Okay, great. Hello guys, thank you very much for the opportunity to talk to you. So I'm gonna like shift gear a little bit back to the agricultural side of things, and I'm gonna be talking about some of the works that we've been doing at the Translational AI Center at Iowa State, and it's also like a collaborative effort with the AI Institute for Resilient Agriculture, which is like an NSF-funded institute, one of the NSF-funded institutes. So this the talk today would be centered around like our ongoing effort into building like a full end-to-end pipeline for weed control, basically. So this is titled like a foundation model-based approach for identification and classification. Okay, to give sort of like a background, I'm sure most of us we know weeds at least in the agricultural settings. Basically, they are like those crops or those plants that compete with the desirable crops, so crops that farmers are interested in, or maybe the agricultural scientists. So these are the other plants in the field that compete with those crops of interest for resources. They usually affect yields, they impact yields significantly, with farmers reporting enormous losses when like fields are not well managed from weeds. And one of the big problems with weeds in particular is that they spread rapidly and they reproduce very quickly. So this also makes it very difficult to control, especially when they are not managed in the initial stages of the growing season. But I'm going to like talk a lot more about this. The fourth point basically is that even as the years have gone by, there's been so many like advances in trying to like manage weeds. But one of the growing problems nowadays is that due to like climate change, due to trade, interconnectivity, there is like a growing trend of weeds like transfer across geographic locations, and like they even growing they're able to like winter whatever management systems is created to control them, so they are able to like withstand each of these. And like this sort of motivates the whole idea that we really need efficient management systems, right? So a lot of the existing systems currently is that farmers just go with their tractors or whatever systems they use to apply herbicides and indiscriminately just apply herbicides across the field. At least that's like the most common approach that most farmers use. But if we are to talk about efficient management, as I said earlier, right, one of the most important and even first step to efficiently managing weeds on a farm is basically identifying those weeds, right? Because different weeds, basically, you control them in different ways because they basically vary in the way they respond to the different management strategies. Some weeds are better crushed, some weeds are better like sprayed with herbicides, and even for those that are sprayed with herbicides, they are like specific kind of herbicides that's needed to control them basically. So on the right side of this screen, you can see like a basic weed identification guide. Basically, the way the traditional way identification is done is that usually maybe the weed scientist or maybe the extension officers, they have like a small book, a small pocket where they use to like match whatever weeds they see in the field, and that would like give them a sense of how best to like advise the farmer to control the weed, right? So this is like a very crude and inefficient methods. So some of our efforts to like making this like a more resilient and sustainable process is what I'm going to be talking about today. And I also mentioned that I did mention that weeds like they compete with crops for resources, right? But I also want to also establish this idea that sometimes weeds do not necessarily hinder the crops. Sometimes there are even weeds that help the crops. So sometimes you want the beneficial weeds that you do not plant there, but they also help the crops you are interested in. So like that's one of the central cases for why you need to like manage them, so you do not just go and spray all the weeds or all the plants in the field. But yes, I know that I have talked about this idea of like managing them and how we need to identify. But one of the problems with efficient identification in this case now is that there are like thousands of different types of weeds, right? And in building like an efficient model or an efficient pipeline to control this, you need data sets. The first two speakers talked a lot about like data sets and annotation and labeling. But in this case, weeds, usually we have like very highly imbalanced weeds. Some weeds are like just very prevalent in a location, and you have like a lot of those, and you have some which are not as prevalent, and maybe over time they start to move in there. When we are able to like identify and create a solution for these problems, we can do like targeted mitigation and limit the control of the beneficial species that I talked about earlier. So I'm going to talk about like the approach of what we are doing, what we've done, and the ongoing efforts. But I'm going to start by giving this bit of introduction that our group at the Translational AI Center at Iowa State, we have built like a similar version of this, which is already deployed, which is called the insect net, basically a pipeline or a model that you could use to identify like thousands of insect species prevalent to agriculture. So if you want to like take a look and like explore around, you could always scan this code or go to the web link. Yeah. So yes, building on top of like our experience with the insect net, right? I did talk about how the first and maybe even the most important steps with building like efficient AI tools basically is the data set. And that's what I'm going to start with for the methodology. Basically, we create like data sets from a citizen science platform called the iNaturalist. It has like tons of biodiversity images across the world, basically, and this spans like multiple species from insects to animals to crops to weeds and all. So it is one of the largest publicly available data sets of organisms across the world. And basically, because of a collaboration between iNaturalist and AWS through an open data sponsorship program, they've been able to like make this data sets, the images, available for like academic research and scientific applications, basically. The problem with this is just that a lot of these images, they just exist in like buckets, AWS buckets. They are not like ML ready. So we did build a pipeline where you could easily use and like download and curate these data sets for all of like your machine learning applications, basically. And just to talk a little bit about what you see when you go to iNaturalist, it is very easy to explore. But for us, what we did was the weed scientists in our team, they basically created agriculturally relevant weed species, basically. So the taxon ID, we were able to like filter from iNaturalist the taxon ID for those weed species of interest. We were also able to select some like level of control on top of the quality of the images that we get, basically. And we also got like the licenses that allow us to work with this and the taxonomy of interest for those weed species. Yeah. So I'm gonna go into the overview of the pipeline basically, and we can just focus on the top box, which is just the training pipeline. So we used a multi-stage method towards our training, basically trying to like use some of the ongoing state-of-the-art processes in training algorithms, like with self-supervised learning, where we start by like weekly uh, self-supervised training the model on Instagram datasets. So basically real-world images and like tons of those. Then we moved to another stage of self-supervised pre-training, basically narrowing down the domain into the like plant domain, basically on millions of images before we then do like the supervised fine-tuning. And for inference, we also explored quantization as a means to making it more efficient in deploy. So to talk a little bit about the training, I'm not going to go into details about the process. I know that the previous speaker did talk a little bit about transformer models. So we used a vision transformer for training this model, basically, and it works by essentially patchifying the images. But the self-supervised training algorithm that we used is masking, where some of these patches are basically masked, and using like an auto encoder framework, we are able to like reconstruct those masked patches, basically. And in our case, we performed the supervised training on about 1,500 samples, training for about 240 hours on 32 V100 GPUs. Okay, to talk a little bit about the initial results or evaluations, as I mentioned earlier, we did start stage one with like some pre-training, or like you can call it pre-training, on basically 3.5 billion Instagram images. That was like the weight we initialized with. Then we moved to the the iNat plant-related images, which are about 14 million images. And for these first two stages, they were just self-supervised training, so they did not involve like any evaluation metrics. But in the fine-tuning case, where we fine-tune on 1,500 classes, basically, we saw about like 90.5% accuracy. And you can see like in the bottom left here, basically the distribution of performance across classes. And what you see here is like how many classes performed as well as like 100%, and how they varied as they go lower. On the right-hand side here, what you see basically is like a comparison between how many training images exist basically for each class, and how that's affected like the per class accuracy. So you can see that for most cases, classes with lots of images did perform higher than the rest. We did see some classes with like lower number of images, even having like close to 100% accuracy on our training set, on our test set. But a good number of them did not do well because there are not so many images. So we had like about 50 images in some of these classes. And although those images, when we try to like explore why some did have high per class accuracy and why some did not, we did see that for some classes with weeds, there are some species that have like very similar looking classes to other weeds, and like maybe they have different roles in the ecosystem, but they look so similar. So for cases where there are like multiple classes, where one has like sufficiently enough number of samples, whereas there's another that has like significantly low number of samples, they fall in this part of the distribution basically. But I'm going to talk about some of the things that we employed to sort of like make this better and like help with the deployment. So another evaluation that we did was, most of these data sets, they were focused on some specific regions. So we did try to evaluate our model on data sets from different parts of the world, and like other data sets that do not fit into the distribution of like the data sets we trained on basically. So we went into the literature and took a couple of data sets that exist, and we tried to do like a systemic evaluation of our model's performance by basically adjusting the number of training samples in that data set. So in the first column here, where k equals to 0, basically this is just like an inference or a test setting where we do not do any training or any fine-tuning of our model, and we just tested the accuracy of the model. And you see that in some cases, the model, especially in this plant seedling V2, the model does not do as well. But in this case, most of the images in this data set had even smaller number of pixels, like in comparison to what our model was trained on. And for example, in this deep weeds data set, also the distribution of the images just look significantly different because of the location of the images were taken and like the type of camera that were used. But what we did notice was that using our model as like the initial step for like very minimal fine tuning, so with as little as say 10 samples, we're able to like bump the accuracy significantly higher in comparison to like just zero shot evaluations, right? And even increasing that with a little bit more as 20, we had like close to 100% accuracy. And definitely using all did provide the highest accuracy. So based on this like idea, right, we knew that for most people that would maybe use this in the field or like in the real world setting, they may not be interested in like the global weeds, right? So we had another version of our model, which is specifically focused on the most prevalent weeds in the Midwest. So we created a region-specific data set of 84 weeds that are just common to the to the Midwest, and we sort of used our model again as to initialize the weights, basically fine-tuning it for this specific weeds, right? And we did see that using our global model as a sort of like the foundation model to start fine-tuning, we saw like a very good accuracy with about a 5.32% gain over just fine-tuning on this data set itself. So this is just like a snapshot of what I just talked about. The first part is the global model, I said, across the world. Some of the other problems I mentioned where I said some classes had very small samples. We had to incorporate some expert data sets, basically, from the literature to sort of supplement. So, one other thing with using the citizen science data sets is that some of the labels that do exist may not be the correct labels because these are not like weed scientists. So we had to incorporate some expert data sets that has been verified. And we sort of saw some gain in performance when we added that to the model. And when we also performed this same thing on our like local model, we did see a similar gain. So as I said, right, we're interested more in the end-to-end pipeline, basically. So one of the efforts that we are currently doing to sort of like make this model available to everyone, so like the farmers, weed scientists, or anyone interested, basically, is we built a web app, basically, where you could just easily maybe take an image or upload any image you took on the field. And you get like a prediction. And we also provide like all the scientific information necessary. So you could get the common name, the class, the taxonomy class, and other information. We also provide like even management information, or how do you detect this? So if you try to learn the morphological features that you'd use to like differentiate it from the lookalike species, which we also provide here. And we also provide like the undesirability and like their role in the ecosystem. So like some weeds, are they beneficial? Are they like a threat to the crop? In addition, what we also noticed was that, with every classification model or any classification pipeline, right, we sort of took our inference and divided them into three stages or three classes, right? The three scenarios possible when you use your classifier in the field basically is you either get a correct prediction. So probably you are testing your model on an image or a type of image, a species that is present in the species that the model was trained on. So, and you get it correctly. That is like one of the scenarios you get. In some cases, you could test it on a species that is not present in the training set, basically. And that gives a wrong prediction, right? Because the model will try to give you an output, but because the weed you're trying to test it on is not even in a training set, that would always be wrong. And in some cases, you could try to test it on a weed species, which is within the training set, and the model does not give the correct prediction, right? But in our bid to make this safer, right, we always attend the farm progress show, which is like a very big event of farmers located in the United States or around the world, where they come to like display some of the advances in agriculture. And some of the feedback we got from the farmers were like, how do we trust these models, right? Like most model, when they played around with most model in the industry, basically they give some wrong labels. So in a bid to sort of like improve trustworthiness of our model and make like deployments even more acceptable, we came up with strategies to basically help this model provide some context, especially when it misclassifies species. So sometimes when a species, say a new species, migrates into a new region, and the model maybe does not have that species trained in them, how does it let the user know that, okay, this does not exist? Or maybe when the model is not even sure about a prediction, how do we let the user know that this does not, the model is not confident about the output? So that leads to the inference pipeline of the chart that I showed earlier. Basically, we have our classification model now. Then we built two wrappers over this classification model. One is the uncertainty quantification, and the other is called the out of distribution detection. And I'm going to explain each of these basically in detail. So, as I said earlier, right, I'm going to give an example. So, at the farm progress show that I mentioned earlier, I think back in 2023, right, we did demo a basic version of what we had built. The thing we did not anticipate was that for some of the farmers that came, some of them came with like their kids, right? And they were trying to like play around with some of these models. And instead of them to like go test the model on like a weed, some of them did take images of themselves. So the kids tried to take images of themselves to see what kind of weeds they are, right? And the model put output some random classes, and like that was like that sort of gave us that indication of like the need to do this to sort of like build trust. Basically, and what this does is basically we came up with a pipeline of like making the model output the probability, or like to let the user know that this data set, maybe when you are trying to make an inference on an image, it does not belong to the distribution the model is trained on. So basically unseen data in a way. And you can see in the image on the right-hand side, basically, if you put like an image of a random object like a car or something it's not trained on, basically the model gives a warning that it has like low certainty on the input image, basically. Although it still gives a prediction, but it comes with this warning, which is not present when the model is within the distribution, basically. The other feature we did build into the model is called the conformal prediction set. And basically, as I said, some species look very similar. For example, when you look at the Avena species, right? So the Avena fatua, which is the wild oat, and the Avena sativa, it is the common oat. These are very similar looking species, although they play different roles in the ecosystem, right? Some are even edible, and I think some are poisonous. So in cases where the model is not able to like give a very confident answer on its output, right? We came up with a wrapper to sort of include the feature where the model can provide other predictions, right? So when a farmer or a user or a scientist uses our model to make inference on an image, and the model is not so confident, it provides like multiple other predictions, and that gives the person like maybe the initiative to basically maybe go confirm or at least use it with caution, right? And this sort of like we did see some notable positive feedback from the farmers. So one other thing we did to sort of democratize the model basically was to incorporate like an LLM feature to the model basically, which we call the Add LLM, and we did go to multiple documents across multiple universities in the United States basically, and we sort of like created documents related to weed management strategies and sort of like used a RAG pipeline to embed this into a GPT model. And we incorporated this with our model, and I'm going to show this closer. So when you make inference on an image, basically on a weed, you can sort of like interact with it on how do you control it or how do you manage it, and like so that it takes it a step further from just a simple inference. And basically, we did wrap all of this together. It's deployed. We have like APIs for the insect model I talked about earlier, and the weed model and the Ag LLM. And we sort of like put this together on an OpenShift cluster. And we package this as a pest ID app where you can either just do insect identification or weed identification and like have conversations with it. Okay, I'm going to sort of like wrap this up with some of like some anecdotal examples of what our weed model can do. Basically, usually when you are trying to manage weeds in the field, you are more interested in, say, maybe early stages weed. So you want to control them before they grow bigger to like impact the crops or focus on the field, right? And so we did an extensive test across the multiple life stages of the field of the weeds, and you can see that even when the weeds are like significantly smaller, our model is able to like identify them, and even when they progress to like later in the growth stage. I also talked earlier about like intra-class similarity, dissimilarity, and interclass similarity. So within some classes, right, as the weed evolve across the growing stages, basically, they look very different. And some classes, multiple classes within the same maybe genus or the same family, they can look very similar, right? So that's also something our model is able to do. But in cases where like it is not as confident as I mentioned earlier, it's able to give those warning signs on its prediction. We also try to explore, in practice, most of the images you're gonna like try to make inference on, they are not necessarily isolated, right? So we have like a lot of green on green weed species. So we did some evaluations on like different occlusion levels and like green on green poses, and you can see that we also have like images or like we've tested on where you do not necessarily have to like zoom on the imaging focus as long as it is like covering the majority of the input image. So we have most of that. We have like different number of leaves and similar targets. So another example I was going to show is basically it's called the grass legume. So when you're trying to identify some grass in the farm, right? As an expert, there are some cues you have to like focus on, right? Although we do not necessarily curate our data set, so we do not have these data sets zoomed in to each of this. We also saw that our model do have the capability to like focus on the parts of the grasses where you use to determine what category they belong to. So this is like sort of like some of the features we noticed that's able. This is also not like 100% correct method. As I said, we have like some failure cases too, which I try to highlight some of them. So finally, we also, as I mentioned earlier, that we are trying to provide a solution, an end-to-end solution, right? We are also like transitioning towards an IPM strategy where we can involve the use of like drones and like ground robots and all of that. So we also did some evaluations on data set collected from UAVs, drones, basically. And what we did was to like go to a field and identify some weeds and watch them. We took images of them as they went through the growing season. So basically, we had like markers to identify target weed locations, and our model is able to like classify this correctly. So I should mention that this is not like an object detection model, but basically we manually did crop each of this out. And as I said, the model was not explicitly trained on these UAV images, basically. And finally, this is sort of like our pipeline. When we are able to like create these weed identification maps and identify what weeds are present, we can send the drones with the specific herbicides. We can go and do like some spot specific application of the specific herbicide necessary. Okay, I'm going to end with a little bit of acknowledgement. So there are like multiple people in this team. And as I said, it's an ongoing effort. We get support from NSF, USD, NIFA, the Iowa State Plant Science Institute. Yeah, I'm happy to take questions. I know that we do not have enough time.